Hey guys, today I will explain what permutations of n different objects taken are at the time mean. Also, I will come up with a couple of examples of this kind of permutations. And also, I will go briefly, concisely through the permutation formula. And at the end, I will come up with a word problem involving permutations of n different objects taken are at the time. Now, I think the best way to explain what does it mean is just take a look at an example. Say you have been given a 5-element set. Let's say you are given a set, let's call it A, and it comes to little bit a set theory, if you don't mind. So let's say set A containing the following elements: A, B, C, D, and let me throw in E. Let's say your set A has these 5 elements. So is composed of these 5 elements. Now, I'm going to select from these 5 elements any 3, let's say, elements. And I'm going to select them, choose them in a particular order. So order does matter. And by the way, I do have a separate video on permutations of n different objects, and the link will be down below in the description box, and you could check this video later. You could jump into this because it's basically related to what I'm talking now. So generally speaking, for all permutation, even if you are given just n objects and all you need to do is just rearrange, and you are rearranging them in a particular order. For all these kind of problems, for all of this kind of stuff, the order in which you have your arrangement, in which you organize your things in a particular fashion, in a particular linear manner, the order does matter. So the order is vitally important, and this is the bottom line of all of this stuff. Now, I'm going to choose, let's get back into this. I'm going to select 3 element sets in a particular order. For example, let's say it's not basically a set in terms of a set theory, in a set language, in a set speak, because if look at this from that point of set conception, the order in which the elements of a normal set are listed does not matter. So in this case, the order does matter. You could think of this kind of a sequence if it helps you, because for sequence, the order does matter. Anyway, I will just show you by using an example. I think that would be the best way. So let's say 3 elements. So I'm going to just select any 3 letters, but in a particular order. And I'm going to use just the normal brackets, because I'm not going to use these curly brackets, because basically curly brackets means that the order does not matter. Anyway, so let me choose any 3 elements. Let's say A, B, C. Now, I could also pick C, B, A. And, as I mentioned before, in terms of a set conception, these elements, they are precisely the same, because we usually consider set in irrespective of order. Now, for permutations, so the order, again, I'm emphasizing this is the bottom line, does matter. And again, if I want to swap, if I want to change another 2 elements, let's say B and C, I would come up with another permutation. So let's say A, C, B, and so on, etc. List goes on, because you could list them out and it would take some time. Again, in this case, my n is 5, since I have 5 elements, 1, 2, 3, 4, 5. And my r, if it comes to the notation, my r, or sometimes is denoted by little k, doesn't matter. So my r equals 3. So I'm going to take or select or pick, if you like, from these 5 elements any 3, and in particular order. I hope I made it clear for you. So I'm doing my best. So you could pick another 3 elements, let's say C, D, E, and it's gonna be another permutation of 5 elements taken 3 at a time. So you could pick another 3, A, C, E, B, D, E, E, B, C, A, D, B. So any 3 in any order, but if you swap the order of any 2 elements, you would come up with a different permutation. Now, in case if you are wondering, could I take any 2 elements? Yes, you can. So taken R at a time, that means R generally less than N. It could be equal to N, but generally it's less than N. So you could pick 4 elements, you could pick 2 elements, even you could pick 1. So, for example, if R equals 2, if I'm going to pick any 2 elements, so your kind of subsets, it's not really subsets in terms of a set conception and set theory, but kind of sequence or list elements, if you will. So it could be like A, B, B, C, D, E, B, A, whatever. So any 2 in any order, you swap order, you change order, and you would come up with the different permutations. Alright, so this is the general idea. So that's why we choose, we pick, we select, we take this R fixed elements or objects or things, if you like, from given N objects. Now, the question might be raised over here, how many these permutations of these 5 elements taken 3 at a time can be made? So how many? So you could basically list them out, make a list, but it would take time, and I believe like maybe 1-2 days. So there is a instantaneous solution. There is a quick formula. It's called a permutation formula, and by the way, I have a separate video on the permutation formula and how to figure out how to, in reality, to use the formula, and the link will be down below in the description box. And if you are down to this, you could just simply jump into this and check it out later. Now, let's just, for fun, for kick, calculate. So how many these 3 elements permutation can be made, can be formed from this 5 element set. So you would simply get this, and again this NPR, or sometimes it's written also this way. It's precisely, I'm just giving you 2 different notations for the same thing. So this symbol generally stands for a total number of permutations of N objects taken R at a time. So, and all that means is just N factorial, so this top number goes on top, over the difference between N and R factorial. And again, long story short, N factorial, it's denoted by N, this kind of exclamation mark. It stands for this long multiplication, so it could be converted into multiplication. So you start with N and you multiply all the way until you hit 1. So N times N minus 1, N minus 2, all the way to, and you end up with 1. And by definition, this is kind of convenient way to take that 0 factorial sometimes when you working out these coefficients, these numbers, whatever. So by definition, 0 factorials is 1. So keep it in mind, because some people mistake it as a 0 and they would go straight with this kind of calculation. So sometimes 0 factorial comes up. So just by definition, it's 1. It's worth to remember. Now, get back to this problem. So let's figure out how many these permutations could be made. So your N is 5, your R is 3, and all you need to do is just figure out this number. So 5P3. You could use either this notation or that notation, completely up to you. I'm mostly like kind of my habit, I'm used to it, this notation, so that's fine for me. You could use this one, whatever. Now, all you need to do is just take this 5 factorial goes on top of your fraction, and you need to find the difference. So 5 minus 3. You just simply apply this formula. So basically you don't need even calculator to figure out this number. I will show you how to do it by hand. So all you need to do is just spell out this 5 factorial. So all that means is just 5 times 4 times 3. You keep simplifying all the way down to 1. Now 5 minus 3 gives you 2 factorial, and it's simply again spell it out 2 times 1. Always for these problems, since you have multiplication on top and you have multiplication on bottom, you would also have the common factors, the common numbers. They would eventually cancel each other out, so cross them out, delete them. So in this case it's 2 times 1 on bottom and 2 times 1 on top, so they will cancel each other out. So, and you would be left with just product 5 times 4 times 3, and all you need to do is just figure out. So 5 times 4 gives you 20, 20 times 3 gives you 60. You see, number appears to be kind of a huge, kind of a large number, and again, so all that means that totally the total number of these 3 elements subset, ordered, I would say, let's put it into this perspective, ordered subsets of 3 elements of this 5 elements set, they are 60. So the number is kind of large. That's why I told you, if you are up to just write it explicitly like I started, so you could take your time. Now let's see how can we use permutation of n different objects taken R at a time for solving word problems. Say you have been given something like this. 3 letters are selected from the word problem to form 3-letter code, and you need to determine or find the total number of different codes that can be made or formed. Now all you need to do is just figure out, so you have your word problem, so how many letters your word consists of. So you have 7 letters basically, so 1, 2, 3, 4, 5, 6, 7. So your n for this problem equals 7. Now from these 7 letters you are going to pick, you are going to choose, you are going to select any 3 letters, and you are going to rearrange them in a particular order, so in different orders. So order does matter in this case. So your R equals 3. So again, you could basically try to write out all of these 3-letter codes explicitly, but it would take you ages, I believe more than 1 day. Anyway, so the question is, so how many different codes could be made? So in terms of a permutation, so all we need to do is just figure out, so how many permutations of 3 elements from these 7 elements can be made. So from this, again, in other words, from these 7 elements we are going to pick 3 elements at a time, and all you need to do is just apply this formula. It's kind of straightforward idea. So all you need to do is just take this 7p3. So again, your n is 7, your r is 3. So substitute, your 7 factorial goes on top of your fraction, and the difference 7 minus 3 goes on bottom of your fraction. And all you need to do is just convert it into multiplications. It becomes just 7 times 6 times 5 all the way. So keep multiplying all the way you hit this one. So times 4 times 3 times 2 all the way to 1. So basically you can ignore this one at this point. It will not affect the whole multiplication, but anyway, 7 minus 3, it simplifies to 4 factorial, and let's spell it out. So 4 times 3 times 2 times 1. And check to see if there are common factors that can be cancelled. And for all of these problems, since you have multiplication on top and on the bottom of your fraction, so there are some common numbers, some same numbers, basically same factors that has to be erased, has to be deleted. And look, at this case, it's like 4, 3, 2, 1 appears on top of your fraction, and also they appear on board, they appears on bottom. So just erase that, cancel them out. So you would be left with this product, so 7 times 6 times 5. So 6 times 5 gives you 30, times 7, and you would be left with 200. So this is 30. And times 7, 210. Total number of permutations that can be made from this word. So again, it could be any 3 letters, let's say P, R, or if you would like to come up with some kind of examples, L, E, M, M, E, L, or B, L or EM, so any 3 letters taken in any particular order. So again, order vitally important, order does matter. Now, I would like to give you, so that's your total answer, that's your total number of 3 different letter codes. Now, I would like to give you the quick another way of solving this problem. I assume you don't know what permutations are, you're not familiar with this, but for this problem you could use a multiplication or counting principle, if you will, if it comes to this. And by the way, I do have a separate video on multiplication rule for combinatorics, and the link will be down below in the description box. If you are down to this, you could check it out, you could jump into this later. So let's say, how can we figure out this problem without using permutations? So say we had this 7-letter word, and we are going to select these 3 letters. So we have these 3 slots. Now, for the first place, I have 7 different choices. I could either go for letter P, or for letter R, or for letter O, or for letter B, blah blah blah, list goes on. So you could basically have 7 different choices to pick, to select, to take your first letter. Now, moving on. For the second space, for the second slot, since 1 letter is already taken, I have the rest 6 combinations, 6 variations, if you like. So the second place could be filled out with 6 different choices. Now, since again 2 letters already chosen, okay, picked, selected, so for the last slot, for the last place, I have only 5 different choices. And all you need to do, according to a multiplication rule or a counting principle, if you will, all you need to do is just multiply through these 3 numbers. So 7 times 6 times 5, and it turns out to be, as you might see, you would have precisely the same answer for this problem. So it's 210 different 3-letter codes could be formed. You could come up using the letters from this word problem. Alright, with this being said, I hope it has been helpful to you. Huge thanks for watching, and train your brain. I know everyone hates maths, but if you like my video, please hit this like, share with your friends, leave the comments down below, and be sure to smash that subscribe button if you haven't, so you will not miss out my new videos.